All right, folks, welcome back to the heart. We're going to do the cardiac cycle in this section. So we did the conduction. You saw how the conduction works between the SA node and the atria, and then the AV node, and then how the AV node sends the signal to the ventricles. And now what we're going to talk about is how that conduction is related to the pumping of blood, or what we call the cardiac cycle.
A single cardiac cycle is made up of the events associated with one heartbeat. Each cardiac cycle takes about 0.8 of 1 second. During each cardiac cycle, pressure changes occur within the chambers of the heart as they relax and contract. As the chambers relax, they fill with blood. This is called diastole. When the chambers contract, the blood is expelled. This is called systole. At the beginning of the cardiac cycle, the atrioventricular or AV valves open. This allows blood to begin to flow into the ventricles from the atria. At the same time, the pulmonary and aortic valves are closed, preventing blood in the pulmonary trunk and aorta from entering the ventricles. Ventricular filling is completed by atrial systole or contraction. This contraction results from a series of events beginning with the spread of action potentials from the sinuatrial or SA node across the walls of the atria. This results in atrial depolarization, which is represented by the P wave on the electrocardiogram, also called an ECG or EKG. Atrial depolarization initiates contraction or systole. Atrial systole is represented by the PQ segment on the ECG. Near the end of atrial systole, impulses from the SA node reach the AV node. At this time, impulses spread from the AV node along the ventricular conduction fibers to the walls of the ventricles. This results in ventricular depolarization, which is represented by the QRS complex on the ECG. The atria repolarize, the walls relax, and they remain in diastole for the rest of the cardiac cycle. Atrial repolarization is not seen on an ECG because it is masked by the QRS complex. In ventricular systole, or contraction, increased pressure in the ventricles forces the AV valves closed. The heart sound associated with the closure of the AV valves is known as S1, often described as lub. With continued contraction, ventricular pressures increase until they are higher than those in the pulmonary trunk and aorta. At this point, the pulmonary and aortic valves open and blood is ejected from the ventricles. Ventricular systole is represented by the ST segment on the ECG. In ventricular diastole, or relaxation, the ventricles repolarize. The T wave on an ECG represents ventricular repolarization. Ventricular relaxation results in decreasing ventricular pressure. During ventricular diastole, blood in the pulmonary trunk and aorta flows back toward the semilunar valves, causing them to close. The heart sound associated with closure of the aortic and pulmonary valves is known as S2, often described as dub. After the aortic and pulmonary valves close, pressure in the ventricles continues to decrease. When intraventricular pressure falls below the pressure in the atria, the AV valves open and the cardiac cycle begins again.
Okay, folks, that's the cardiac cycle. Now let's just step through it. All right, so we're starting at A, where everything's relaxed. So atria and ventricles are in diastole, but it's time 0, so the SA node is firing. All right, so what happens at time 0 here is the SA node fires and the atria contract, and that's called atrial systole right here. Now this takes about 100 milliseconds, as you can see right there. Now the atria contract and they force blood through these atrioventricular valves into the ventricles. But the reality is this: during diastole, when everything's in diastole back in here, I'll erase that in a second, but back in here, blood's coming back. And it actually is passively flowing into the ventricles anyway because those valves are open. So what atrial systole does is just pushes whatever blood's still in there. into the ventricles, but the ventricles already have blood in them because there's been this passive filling during total diastole. So I just want you to realize that, because when we talk about Starling's law of the heart, we're going to talk about that passive filling. So atrial systole, the atria contract. While the atria were contracting, the ventricles were in diastole. The ventricles were in diastole right here, as you can see. Well, that's systole, the turquoise color one. The ventricles were in diastole right here, ventricular diastole. And there was a 100 millisecond pause at the AV node that gave the atria time to contract and get all that blood into the ventricles. And there's your 100 millisecond pause. Now the AV node fires and it goes down the Purkinje fibers out to the ventricles. And I go into ventricular systole. Ventricular systole right here. This is when the ventricles contract. Now, a couple things have to happen when these ventricles contract. One thing is, atria goes into diastole. So I'm in atrial diastole. My atria relaxed. The pressure builds up in these two ventricles, and it builds up high enough to shut these AV valves. Back pressure against the AV valves shuts them, so they're closed. And as pressure builds up, I get enough pressure to open the aortic semilunar and the pulmonary semilunar valves. And it's not until the pressure gets high enough that they actually open. So as the ventricles contract, they shut the AV valves and they open those semilunar valves. And then the ventricles go into diastole, and from right here to right here, everything's in diastole. This is when the heart's filling with blood. Right in here when atria and ventricles are in diastole. You'll notice that it's about half of our entire cardiac cycle. So the pumping is quick. And we have the pumping of all four chambers takes only about half the time. And that means the conduction system and the contractions only take about half the time. The other half of the time within a cardiac cycle is filling with blood. All right, so that's the atrial systole. This is showing you atrial systole ends and atrial diastole begins. Showing you that. And then now ventricular systole, and it's opening the semilunar valves, so we're stepping through that. You see the ventricles contracting. I'm wondering why it has two phases here. Oh, I know why. Here's why. And I even alluded to this when I talked about it. When the ventricles start to contract, there's enough pressure to close the AV valves, but there's not yet enough pressure to open the semilunar valves. So in the first phase of ventricular systole, my AV valves have closed, but my semilunar valves have not yet opened. This is actually called isovolumetric contraction. It's called isovolumetric contraction because you're not moving any volume. It's the same volume, but you're contracting. But then with this isovolumetric contraction, you're certainly building up enough pressure to open the semilunar valves, and then you eject the blood. This is where you have blood ejection into your pulmonary arteries and aorta. And then everything's at rest and refilling with blood. And then you do it all again. And that's the cardiac cycle. About 800 milliseconds. This is a collage for you, walking you right around it. I would become very familiar with this because I'm going to use a graph on the test to ask you these questions. Matter of fact, this is half of the graph I'm going to ask you. There's the other half. There's the whole thing. This graph is on your test. Not filled in, though. None of the answers are filled in. So let's talk about this graph for a second. First of all, look at two different graphs, really. We have a y-axis of pressure on the top graph, and we have a y-axis of volume, left ventricular volume, on the bottom graph. These graphs can be superimposed on each other, which means the timeline is the same. So they're two different graphs with two different y-axes, but the x-axes are shared and the timeline is the same. All right. On the top graph, let's look at what these different colored lines are. The black line's the aorta. The blue line's the left atrium. And the red line is... What is the red line? The red line is the left ventricle. The red line is the left ventricle. All right, let's talk about it. Number one right here, this is where I'm about to start atrial systole. So atrial contraction begins right here at number one. How do I know? Well, pressure goes up in my left atrium. See how the pressure just went up? The only way pressure went up is I contracted. So number one is atrial contraction. Number two is I am injecting blood into my ventricles. And you're going to say, well, how do you know that? Move yourself down. Look how my volume in my ventricles is increasing. Well, why would that volume be increasing? Well, remember they fill passively, and actually number one down here is the passive filling of the left ventricle. But why would number two sharply spike? Because my atria contracted. All right, down here, atrial systole ends and ventricular systole is starting. So this is atrial diastole and ventricular systole. So my ventricle starts to contract and it starts to increase pressure. All right, so when that happens, what happens to the AV valves? They close. Number three, I can hear the sound called lub because my AV valves closed. And it even says it right there. Then right here, number four is called an isovolumetric contraction. Isovolumetric. Because the ventricle is contracting, but it's not moving any blood, so the volume's staying the same. And in fact, if you take this number four and draw a line down, you see that I'm not changing volume at all. You see that very shortly I'm going to be, my volume drops off. But right now, I'm not changing any volume, but my pressure is going sky high. Isovolumetric contraction. All right. Enough pressure builds up that my aortic semilunar valves open. Right here is when there's enough pressure to open the aortic semilunar valves. Now I start moving blood. So number five is ejection. This is blood ejection. Ventricular ejection. I'm pumping the blood from my left ventricle into my aorta. Look at how the pressure in my aorta climbs. Look at my black line. Pressure in my aorta is climbing. Why would that be? Because I'm putting blood into it from my left ventricle. Look at how the volume down here, I'm down on the bottom now. Look how the volume of my left ventricle is decreasing. Why would that be? Because I'm pumping blood out of it. Okay, next half of the graph. Oh, before I go on. At the end of diastole, when everything's at rest, at the end of that, at the end of ventricular diastole, because I'm only talking about the left ventricle here, ventricular diastole, how much blood I have in my ventricle at the end of ventricular diastole, that means right before ventricular systole, is called the end diastolic volume. And let's say, and it's saying it's 130. So my end diastolic volume of my left ventricle was 130 milliliters of blood. Okay, let's keep that in mind. All right. Now what's happening is this. I pumped blood into my aorta and pressure in my aorta went up, and there's no more blood left in my left ventricle, or very little anyway. So the pressure in my aorta is greater than the pressure in my left ventricle. And when that happens, my aortic semilunar valve closes. But something very peculiar happens there. It's actually not that peculiar. If you've ever been to the dome or any kind of pneumatic building that's held up by high air pressure, you know that when you open those doors, air rushes out. A big wind funnel of air comes rushing out of those doors, and that's why they have those special circular doors so you don't lose pressure. And but when you do open those doors, when you shut them, you get this jump in pressure, and you can feel it in your ears, and before it equilibrates back to the normal dome pressure. And that jump in pressure is just because you were dropping pressure and you suddenly shut the doors and the pressure just jumped before it stabilized. Well, we see that here in the heart. When the aortic semilunar valves close, the pressure in the aorta just jumps for a second. It just jumps up and then starts declining. Why is it declining? Because blood's moving down through my aorta and out to all the other arteries and pressure's declining. But that jump right there creates a notch, and we call that notch the dicrotic notch. So that notch is there because of the jump in aortic pressure when the aortic semilunar valves shut. All right, this is relaxation right here. Remember that the red line is the left ventricle, and you can see that the pressure is dropping in my left ventricle, so it's left ventricle relaxation. And then I get down here when the pressure's low enough in my left ventricle, the left AV valve opens. And now I can have passive filling. And what do I mean by passive filling? Well, blood's coming back to my atria, and my AV valves are open, so why wouldn't blood flow from my atria to my ventricles? And the answer is it does. So this whole time from here to here, I have passive filling. Now, the jump right here is when the atria contracted, I have active filling of my ventricles because my atria contracted because I start the cycle over again. But in here, I have passive filling. All right, let's look at all that together and then look at end diastolic volume again. Let's look at something down here. We have 130 milliliters of blood in our ventricle, and when we pump it out, we're left with 50. We didn't pump it all out. We didn't go from 130 to 0. We went from 130 to 50. 50 is the end systolic volume. 130 was the end diastolic volume. Well, what's my ejection fraction? Well, my ejection fraction is how much blood I pumped over how much blood total. Well, I didn't pump 130. I pumped whatever 130 minus 50 is. I pumped 80 milliliters. So what's my ejection fraction? 80 over 130. What is that? I don't know. 60% maybe? Something like that. 0.6, I mean. So you do the math. Just do the math for yourself. Do 80 over 130. I actually have a calculator right here. Let me pull out my handy dandy calculator, folks. I'll do it for you. .615, so 61.5%. This equals 0.615. That's 61.5% ejection fraction. I pumped out 61.5% of all the blood that was in my left ventricle. I pumped out 80 and I had 130. That's 61.5%. So some was still left in there. All right. This graph is on your test. Make sure you understand it. Make sure you understand the lubbed up. The sounds. Oh, by the way, I don't think I hit that on the other side. Here's the dub. Dup. Some people say dup. Some people say dub. I think your book says lub dup. I think that's what your book says. So this would be the AV valves closing. This would be the semilunar valves closing. So lub dup. Those are the sounds. Okay, again, folks, this graph is on your test. This is also, your book's kind enough to show you where you put your stethoscope, where you can, to auscultate. Auscultate means listen. I'll put this word up here. So where do you put your stethoscope? Well, there happens to be a whole bunch of different heart sounds, not just two of them. There's not just S1 and S2, which is lubbed up. Yeah, your book does say dup, see? Lubbed up. So there's other sounds also, and I don't know them. I'm not versed in them. If any of you guys are, and I think some of you are EMTs, paramedics, you know these sounds. If any of you have some other similar type of job, then I'm sure you know these sounds. But the S1 and S2 is all I'm going to ask you about. So you're responsible for the lubbed up, but not the other sounds that you can hear. See you in the next section.